This procedure isolates specifically glycosylated glycopeptides from human plasma. Plasma is digested with trypsin to yield a mixture of peptides and glycopeptides. Glycopeptide standards, positive and negative controls for lectin chromatography, are spiked into the plasma. The sample is subjected to high-pressure, liquid chromatography-based lectin affinity chromatography. The lectins used bind to fucose and sialic acid, respectively. Peptides and irrelevant glycopeptides elute from the column in the flow-through fraction. Acetic acid is used to elute the bound fraction from the column. This is enriched for specifically modified glycopeptides.
Hi, I'm Penny Drake from the laboratory of Susan Fisher in the Department of Obstetrics, Gynecology, and Reproductive Sciences and the Sandler Moore Mass Spectrometry Core Facility at the University of California, San Francisco.
And I'm Eric Johansson, also from the Sandler Moore Mass Spectrometry Core Facility and the Fisher Lab.
Today, we will show you a procedure for performing lectin chromatography to enrich glycopeptides from human plasma and other complex mixtures.
We use this procedure in our laboratory as a general tool that has numerous applications. For instance, it plays an important role in our breast cancer biomarker discovery workflow.
So let's get started.
To begin this procedure, wear a mask to protect against inhalation of the beads, then weigh out 100 milligrams of porous beads and transfer to a clean Eppendorf tube. Approximately 300 microliters of beads are needed to pack one column. Additionally, weigh out unconjugated lectin and transfer to a clean Eppendorf tube. The lectins SNA and AAL are used. Proceed to add PBS to the lectin to form a 5 to 20 mg per milliliter solution. Reserve 25 microliters of this pre-conjugated solution. Next, wash the porous beads by adding 1 milliliter of PBS and centrifuging in a microcentrifuge at maximum speed for 3 minutes. Remove the supernatant and repeat the wash. Now work in the fume hood and transfer the remaining lectin solution to the washed porous beads. And add sodium cyanoborohydride to a final concentration of 50 millimolar. Note that sodium cyanoborohydride is toxic and waste must be disposed of appropriately. Secure a closed tube with parafilm and place on a rocker to react overnight at room temperature. After the overnight binding of the lectin to the porous beads, pellet the porous beads again. Remove the supernatant and save as the post-conjugation solution. To block the remaining reactive sites on the beads, first wash the beads by centrifuging with 1 milliliter of quenching buffer, made up of 1 molar tris-Cl at pH 7.4. Then, add 1 milliliter of quenching buffer and sodium cyanoborohydride to a final concentration of 50 millimolar. Place the tube on a rocker and incubate at room temperature for 30 minutes. Quenching is now complete. Centrifuge the beads as before, remove the supernatant, and proceed to wash the beads 5 times with 1 milliliter of 1 molar sodium chloride each time and discard the supernatant. Perform a protein concentration assay on the pre-conjugated and post-conjugated lectin solutions and use the difference to determine the amount of protein that was conjugated to the porous beads. Target lectin concentrations are between 2 to 20 milligrams per milliliter, calculated as the amount of protein conjugated per bead volume. The conjugated porose beads are now ready for packing into a column. To pack the beads into a column, assemble the packing system made up of 2 columns supported on a metal ring stand. The upper column serves as a reservoir for the packing material. The packing system consists of, from bottom to top, pressure restrictor, end column coupler 1, frit, the target column, end column coupler 2, column connector, end column coupler 3, the reservoir column, end column coupler 4, and end fitting. Next, resuspend the 300 microliters of porose beads in 600 microliters of buffer A for packing 1 column. Transfer the beads into the upper reservoir column. Add buffer A until it reaches the top of the column. Gently place the end fitting onto the top of the column, trying to avoid air bubbles in the column. Connect the end fitting of the upper column to the HPLC system. Pack the column by flowing buffer A or PBS through the system. Start with a flow rate of 0.5 milliliters per minute. Increase the flow rate by 0.5 milliliters per minute each minute until either 4 milliliters per minute or the maximum pressure has been reached. Continue at the maximum possible flow rate until at least 35 milliliters of buffer have passed through the column. When finished, turn off the pumps and allow the pressure on the column to drop below 20 psi. Now that the column is packed, gently disassemble the packing system, starting from the top. When reaching the end column coupler 2, remove it carefully. Using a razor blade, gently wipe away the packed material extruding from the top of the column. Do not apply pressure to the beads while doing this. Disengage the packed column from the ring stand. Place a new frit into a new end coupler and turn the packed column over to connect this with the frit plus end coupler on the open column end. The column is now ready for the HPLC run. When not in use, the column can be stored in PBS with 0.5% sodium azide at 4 degrees Celsius for up to 6 months. The details of programming your HPLC will vary according to your setup and the specifics of the manufacturer's software. Here, we use a Microme Paradigm MG4 HPLC. On this machine, methods are built and accessed under the Setup tab at the top of the screen. Program the method shown, which is also described in detail in the accompanying written protocol. If using an autosampler, program it following the written protocol as well. Use buffer A, as before, and buffer B for running the HPLC, and keep the buffers, as well as the columns, at room temperature. Program the UV detector to read at 280 nanometers from 0 to 19 minutes and 50 seconds. Adjust the Y-axis to detect low absorbance levels in the range of 0 to 50 absorbance units. Next, prepare the samples. The test samples are derived from human plasma, depleted of the 14 most abundant proteins, using a Mars column. The depleted plasma samples and 2 standards, human lactoferrin and yeast invertase, are each individually trypsin digested and desalted as previously described. To neutralize the samples, have neutralization buffer ready in the sample vials that will collect eluate. For the Paradigm MG4, 1 vial collects the flow-through and 3 collect the eluate. It will require approximately 1.5 milliliters of buffer to neutralize 1 milliliter of eluate. the target neutralized pH is 7.0 to 8.0. Make sure to test the final pH with pH indicator paper. Desalt the samples as described later in this protocol and resuspend the sample in 1 milliliter of buffer A. For best results, perform 3 experimental replicates so that data may be compared and combined. To prepare samples for 3 replicates, add 3 picomoles of trypsin digested invertase and 1 microliter of HPLC purified lectin-specific lactoferrin to 30 microliters of Mars-depleted trypsin-digested plasma equivalents, or PE. This amounts to approximately 50 micrograms of plasma protein used for each replicate. Add buffer A to the sample to reach a final volume of 330 microliters or 110 microliters per experimental replicate. Using either the AAL or the SNA lectin column, first run 2 blank methods injecting only buffer A. Ensure that the lectin column corresponds to the lectin-specific lactoferrin, used as a standard and previously purified. Chromatograph the 3 plasma samples, injecting a blank in between each injected sample, for a total of 7 HPLC runs. Fractions from blank runs need not be collected. Again, make sure to neutralize the samples by having neutralization buffer present in the sample vials that collect eluate. After desalting and PNG-ACE-F digestion, the samples will be ready for mass spectrometric analyses. Use one 1 milliliter Waters Oasis HLB SPE cartridge for each of the HPLC fractions from the lactoferrin standard and the experimental samples. To desalt, start by attaching the number of required cartridges to a vacuum manifold. Wet each cartridge with 1 milliliter of 80% acetonitrile in 1% formic acid. The vacuum gauge on the manifold should read 5 to 20 inches mercury. Equilibrate the cartridges with 1.5 milliliters of 0.1% formic acid. Again, the vacuum gauge on the manifold should read 5 to 20 inches mercury. Load the entire volume of one sample onto one cartridge. Now the vacuum gauge on the manifold should read 2 to 2.5 inches mercury, and the flow rate should not exceed 1 milliliter per minute. Wash the cartridges 3 times with 1 milliliter of 0.1% formic acid. Using a single labeled collection tube for each cartridge, elute the glycopeptides with 1 milliliter of 80% acetonitrile in 0.1% formic acid. Neutralize the eluate by adding 60 microliters of 0.5 molar ammonium bicarbonate to each collection tube. The target neutralized pH is 7.0 to 8.0. Make sure to test the final pH with pH indicator paper. Concentrate the eluted peptides to approximately 50 microliters by using a vacuum centrifuge, such as Thermosavant SpeedVac, for approximately 2 hours at 35 degrees Celsius. Again, test the sample pH after concentrating to ensure it is between 7.0 to 8.0. If needed, add 50 millimolar ammonium bicarbonate to increase the pH. If the final sample volume is larger than 100 microliters, concentrate the sample by vacuum centrifugation until it is between 50 to 100 microliters. Finally, remove N-linked carbohydrates from the peptides by adding 250 units glycerol-free peptide N-glycosidase F, or PNG-ACE-F, to each sample tube, and incubate at 37 degrees Celsius overnight. Following the overnight incubation with PNGASF, use zip-tip pipette tips containing a reverse phase C18 matrix to dissolve the samples. Before beginning, make 2 droplets, one of 0.1% formic acid and one of 80% acetonitrile plus 0.1% formic acid on a piece of parafilm for washing and eluting. Droplets are used to prevent cross-contamination of peptides between samples, and new droplets are prepared for each zip-tipped sample. Start by wetting a zip-tip with acetonitrile solutions. Equilibrate the zip-tip by pipetting up and down with 10 microliters of 0.1% formic acid 3 times. Load the sample by pipetting up and down 10 times, then wash the tip with 10 microliters of 0.1% formic acid 5 times. Finally, elute the sample twice with 80% acetonitrile in 1% formic acid. Collect eluted peptides in an Eppendorf tube. Reduce the sample volume to less than 2 microliters by concentration in a vacuum centrifuge. And finish by resuspending the samples in 20 microliters of 0.1% formic acid. The samples are now ready for analysis by LC-MS. The porose conjugation typically yields on-bead lectin concentrations in the range of 2 to 20 mg per milliliter, which is optimal for affinity chromatography. Lectin chromatography of trypsin-digested, Mars-depleted human plasma typically enriches glycopeptides in the bound fraction. Our workflow identifies N-linked glycopeptides, which contain the N-linked consensus sequence NXS or NXT, where X is any residue except proline. PNGASF treatment removes the N-linked glycans and deamidates the asparagine residue to which glycans were attached. Deamidation results in a 1 Dalton mass shift of the deglycosylated peptide, or deglycopeptide, from the unmodified peptide. Thus, deglycopeptides are identified as peptides containing the N-linked consensus sequence, where the asparagine residue within the consensus sequence is deamidated, observed as a mass difference of +1 compared to an unmodified asparagine residue. Here, 2 example spectra illustrate this concept. The top spectrum shows the fragmentation of an unmodified peptide containing the N-linked consensus sequence. The bottom spectrum shows fragmentation of the same peptide with a deamidated asparagine residue within the N-linked consensus sequence. The circled molecular ions from the Y7, Y8, and B3 fragments of the deamidated peptide are increased in mass by 1 Dalton, as compared to their counterparts in the unmodified peptide. This mass shift indicates that the peptide in the bottom spectrum contains a deamidated asparagine residue. Typically, using a Q-star elite, 1,000 to 1,300 total peptides will be identified in the flow-through fraction, and 200 to 400 peptides will be identified in the bound fraction. On average, the flow-through fraction from AAL or SNA chromatography contains 2 to 4% deglycopeptides, whereas 30 to 50% of the peptides recovered in the bound fraction are deglycopeptides. We use the term deglycopeptides rather than glycopeptides, as the deglycosylated deamidated molecules are observed during mass spectrometric analysis. However, we propose that the majority of deglycopeptides in our samples were previously N-linked glycopeptides that were deglycosylated and deamidated by PNGASF treatment. The enrichment of deglycopeptides in our bound sample supports this hypothesis and allows us to use detection of deglycopeptides as a proxy for the glycopeptides captured by our lectin affinity chromatography protocol. 2 or more distinct invertase deglycopeptides should be observed in the flow-through fraction, and 2 or more distinct lactoferrin deglycopeptides in the bound fraction.
We've just shown you how to prepare lectin columns and perform lectin affinity chromatography in an HPLC format.
When doing this procedure, it's important to start out with high-quality glycopeptide samples, to monitor the pH of your samples throughout the experiment, and to confirm the quality of your chromatography with glycopeptide standards.
So that's it. Thanks for watching, and good luck with your experiments.